Hey folks, so in this video, I'll introduce the two coloring problem. So this problem is basically a math problem, right? So it's well, it's mathematically interesting. Now we're going to look at kind of a simpler version of the problem, which is straightforward, but there are reasons why people consider this to be an interesting problem. All right, so this is called two coloring. This is kind of a specific version of what they call the K coloring problem. So the idea is this: given a graph, can I color the nodes in it with different colors such that no node pair has the same colors on it, right? Looking at this graph here, what I basically see is a two-colored graph, right? So I have 5 different nodes. I'm coloring basically gray and red, and you'll realize, right, that there are no gray nodes next to gray nodes or connected to gray nodes. There are no red nodes connected to red nodes, right? So everything looks good there, right? This is a two-colorable graph. If I had another edge in here, like for example, if I had an edge from 1 to 4, then it would be a different story, right? If I had that, this would no longer be a two-colored graph because, well, I have two things that are paired together, but they have basically the same color, right? So that's no longer a two-colorable graph. So what I want to basically try to figure out, right, is if a graph is sort of colorable in any sense, right? So I want to know if I have the option of basically coloring these nodes in some way, right? And I could have maybe different number of colors, right? So I could have, 3 colors, 4 colors, 5 colors. Right now we're talking about the simplest case, which is just to two-color it. So our question might be asked like this: how do I two-color a graph? Well, what I'm going to do, right, is basically, hopefully, right, I can, well, the question I guess is, can I two-color a graph, and then how do I do it, right? So in general, we can kind of put those together, right? We can basically attempt to color a graph, and then if I don't color it properly, then I can say, okay, it wasn't too colorable, right? So how can we do that, right? How can we check to see whether a graph can be labeled in such a way that no nodes that are connected have the same label or same color on them, right, in different pairs? So what do I do here? Well, what I can basically say, right, is I can say, you know what, I'll start with DFS, right? And DFS looks at a graph and starts to explore through it. Well, initially, I can say, DFS, the very first node you explore, give it a color. Give it a color, for example, gray. Okay, that's fine. And then DFS will run its little loop inside, and what you can basically say is, whenever you go and see something new, right, a new neighbor, do the recursive call on them, and also mark them with a color that's the opposite of the one you already are, right? So basically, it's like every time you make a recursive call to go explore somebody else, you just flip the color that you're putting on them, right? So when you mark them, you also put the color on them, and the color is always the opposite of the last one you put on, right? So you can do that. But then, that's not enough by itself. And so in addition to that, what you also need to do is when you see a node that's marked, check its color, right? So check its color, and if its color is not the opposite of the one that you currently are exploring from, then it's, I've already colored it, and it's colored in a way that doesn't suit me, so it's no longer too colorable, okay? So yeah, and I can basically continue doing that, right? I can try basically whenever I run DFS to always put on different colors, and then whenever I see something I've already seen before, I can check to see whether the color is the appropriate color or not. And if it isn't, well, then I'm stuck, right? And it's not too colorable. If I get through the entire graph and I'm able to put all those labels, well, then everything is good. I've managed to two-color my graph. All right. So this problem here, so the two-coloring maybe seems a little bit arbitrary. There are some practical usages of it. This is actually somehow has some usages in, again, it's going to be in like network reliability. Somehow there is the idea of like, maybe you could have these two different colors represent like categories of things, right? It's like, well, I want to make sure that, I have, two devices, right? It's like, well, if I lose 2 of this type, then I'm in trouble. If I lose 2 of this other type, I'm in trouble. So maybe somehow if I have the two coloring, I can make sure these devices are never next to each other, because if I have damage in an area, I don't want to take out 2 of the same thing. I want to take out 2 different things, right? So if I can properly two-color a graph, that means that things are kind of distributed, right? My colors are distributed throughout my graph, so that if I have some faults somewhere, I hit both things rather than just one thing, right? Because maybe that's the issue. Maybe I wanted to prevent losing all my red nodes, right? Maybe that's my trouble, right? My problem, right? It's okay if I lose some red and some gray, right? Then I can recover from it, right? So there's some reliability things that I can basically have here. The other note about this problem is that this is so this is the simple case, right? This is two coloring, but the more general case is this one over here we mentioned of K coloring. And K coloring is notable for the following reason. Two coloring a graph is straightforward. One coloring a graph is also straightforward. 3 coloring a graph is maybe a little bit harder. 4 coloring a graph is impossible. Okay, so all of a sudden, right, this coloring problem, as you increase that number over here, what you actually get is you get what they call an NP-complete problem. So we kind of mentioned this a little bit back in analysis of algorithms. Basically what it is if I want to check to see whether a graph is 4 colorable or 5 colorable or some higher number colorable, the amount of work I need to check to see whether that graph is colorable is just exponential, right? I don't have any choice but to try every single combination. And so because of that, right, this is a problem that's an NP complete problem, and so it's going to take, basically forever to run, right? So somehow right here, there's the idea of I started with a problem that maybe is relatively simple, right? Two coloring it, right? And as I increase the number of colors, it gets a little bit more complicated. But all of a sudden, right, you get too far, and all of a sudden, just in a single moment, you all of a sudden end up with a problem that is downright impossible. Okay, so that's another reason why coloring is a little bit interesting, right? It goes from something that's being very straightforward to all of a sudden being something that's almost impossible. All right, so that's all I got for two coloring. So yeah, this is kind of another application of kind of graph. Well, it's another application of using our algorithms, right, DFS and BFS, to solve a problem that's more on the theoretical side. It's more on the graph theory side. All right, so that's all I got for you guys. I will see you guys in the next module.